A subtle dip in fluid force ripples through 50 miles of dark, buried steel pipe, moving faster than the fluid itself. For decades, a drop like this would go completely unnoticed until millions of gallons escaped into the surrounding soil. Today, a modern steel body houses microsensors mounted directly inside the flow path. These solid-state devices read fluid thrust 10,000 times every second, turning mechanical physical stress into instant digital data. In earlier decades, pipeline integrity depended almost entirely on manual checks by human workers walking remote corridors. Maintenance crews drove truck routes along endless miles of remote right-of-way, carrying portable gauges and logging local dial readings by hand on paper clipboards. By the time a physical leak caused an obvious surface pool or a massive drop in line delivery, damage was already severe. The delay between a physical rupture and an operator manually turning a heavy handwheel often stretched across many hours, leaving vast landscapes exposed to toxic contamination. The core issue with ancient monitoring was the sheer latency of human reaction time and coarse analog instruments. Early supervisory systems used simple telemetry that updated only every few minutes, leaving wide operational blind spots. Small pinhole breaches or slow joint failures went completely undetected under normal operating variants. To protect critical fuel and water networks, industrial engineers needed an edge device that could think, evaluate, and act directly at the site of the pipe wall without waiting for a distant human operator to read a screen. That urgent mechanical need gave birth to the modern smart valve. These units are not mere mechanical gates that open and close on simple command. They are integrated edge computing stations. Embedded inside the heavy cast steel housing site piezo-resistive silicon sensors and low-power microprocessors sealed in explosion-proof enclosures, powered by local solar panels, energy harvesters, or direct lines. These sensors record fluid force, flow velocity, ambient temperature, and structural vibration in real time. The primary diagnostic tool used by these intelligent units is high-frequency pressure transient analysis. Whenever a sudden leak, valve closure, or pump failure occurs, it creates a tiny kinetic shockwave within the moving fluid column. This dynamic disturbance travels outward through the medium at the speed of sound, which can exceed 3,000 feet per second, depending on fluid density. The internal sensors pick up these micro fluctuations long before a broad volume drop becomes visible on standard meters. By capturing these transient acoustic waves at microsecond resolution, the onboard microprocessors compute the exact wave shape and arrival timing. When a wave hits multiple smart nodes along a single pipeline, edge algorithms compare the precise timestamps generated by local high-accuracy clocks. Using these minute arrival time differences across fixed distances, the automated system calculates the exact location of the structural breach down to a few yards along a pipeline stretching across hundreds of miles. Once a pressure anomaly passes local thresholds, the smart valve does not wait for remote human permission to respond. The local microcontroller evaluates the incoming pressure transient analysis against trained operational profiles stored in its onboard flash memory. If the data signature matches an active pipe break rather than a normal pump start, the unit commands its electro-hydraulic actuator to initiate an immediate automated shutoff. Heavy steel discs or rotating spheres turn against the violent flow, sealing the pipe segment in seconds. This transition from manual checks to real-time, sensor-driven automated shutoff systems fundamentally changes industrial safety margins. Instead of dumping crude oil, toxic chemical feedstocks, or high-pressure gas into farmland for half a day, the affected line section isolates almost instantly. The total volume released is restricted solely to what remains trapped between two adjacent smart valves, reducing potential environmental disasters from million-gallon catastrophes down to controlled, manageable, contained spills. To maintain this level of constant vigilance, smart valves rely heavily on robust IoT sensors connected through resilient communication networks. Local radios utilize cellular, satellite, or low-power wide-area protocols to transmit continuous health telemetry back to central infrastructure hubs. Even if primary satellite links fail during severe weather or power outages, these industrial edge devices retain total local autonomy, making life-saving safety decisions independent of external network connections. The transition toward total edge autonomy required decades of hardware refinements across harsh industrial environments. Early electronic valves built in the 1980s and 1990s suffered from constant false alarms caused by simple pressure surges, thermal expansion, or standard pump cycles. Operators frequently disabled early automated trip routines because bad data constantly shut down active supply lines, causing costly industrial downtime. Modern digital signal processors solve this issue by filtering out background fluid noise through advanced digital algorithms. In vast transcontinental networks carrying critical natural gas, a single unmanaged rupture can disrupt fuel supplies for entire industrial cities. Traditional pipeline monitoring depended heavily on basic mass balance calculations, which simply subtracted outgoing volume from incoming volume. However, because gas expands and compresses based on ambient thermal changes, mass balance formulas often took hours to confirm a true loss, permitting massive leaks to spew uncontrolled, while engineers debated whether the discrepancy was real or just a temperature shift. Smart valves eliminate that thermal guesswork by combining pressure transient analysis with density and temperature compensation at the physical sensor head. By measuring local liquid density alongside high-speed pressure shifts, the embedded logic board continuously updates the fluid dynamic baseline of the pipe segment. The system immediately distinguishes between an intentional operational flow change and a sudden structural breach, removing the ambiguity that historically delayed critical emergency shutdowns. The physical mechanics inside these smart valve bodies are engineered to withstand extreme forces without failing. High-torque electric motors or spring-loaded hydraulic reserves provide the immense mechanical energy required to force heavy internal plugs closed against fluid moving under thousands of pounds of pressure per square inch. Dual independent position sensors track the precise degree of valve stem motion, confirming that the mechanical barrier has fully seated against its hardened metal ring. Beyond emergency shutoff actions, these edge units continuously monitor their own internal mechanical wear. By tracking the exact electric current required to turn the valve stem during routine exercise cycles, the internal microprocessor detects subtle mechanical binding, seat erosion, or seal degradation long before a total hardware jam occurs. Predictive maintenance software flags these minute physical changes, allowing field technicians to replace worn internal seals during scheduled maintenance visits rather than responding to an active failure. While oil and gas pipelines drove much of the early innovation, municipal water systems now rely heavily on smart valve infrastructure. In aging municipal networks built in the early 20th century, clean drinking water losses through hidden underground pipe leaks often exceed 30% of total treated volume. Installing sensor-driven valve nodes across complex urban water grids allows cities to automatically balance water pressure overnight, preventing old cast iron pipes from bursting under quiet off-peak pressure spikes. From a global logistics perspective, energy security hinges on the continuous, uninterrupted operation of millions of miles of underground steel lines. A single catastrophic pipeline rupture can halt regional refineries, trigger sudden fuel shortages, and cause economic ripple effects across international markets. Sensor-driven automated shutoff devices serve as the silent guardians of this critical energy backbone, guaranteeing that local structural failures do not cascade into widespread economic gridlock. Because these critical infrastructure devices possess direct physical control over high-pressure energy channels, cybersecurity is built directly into their silicon architecture. Modern smart valves utilize hardware security modules embedded on their circuit boards to cryptographically authenticate all incoming commands and firmware updates. Even if an unauthorized party intercepts transmission signals along remote wireless links, the valve hardware rejects unverified control packets, preventing malicious remote overrides of key infrastructure nodes. In extreme environments like subsea offshore wells or frozen Arctic tundra, human physical access is virtually impossible for months at a time. Smart valves installed on subsea manifolds thousands of feet below the ocean surface operate under enormous external water pressure and freezing temperatures. These isolated underwater units run continuous self-diagnostic routines, autonomously managing fluid flow and isolating seabed leaks without requiring specialized deep-sea repair vessels to deploy remote diving equipment. The economic and environmental savings brought by this technology are immense. Environmental regulatory agencies around the globe now increasingly mandate real-time pressure transient monitoring and automated isolation systems on all newly constructed high-consequence hazardous pipelines. Insurance underwriters similarly reward operators who replace old manual checks with certified smart valve architectures, offering significantly lower liability premiums to facilities that feature rapid, autonomous leak isolation systems. Power management at these isolated pipeline locations represents a major engineering achievement. To operate reliably off the main electrical grid for years without battery replacements, smart valve systems employ low-power microcontrollers that sleep between high-speed sampling cycles. Thermoelectric generators mounted directly to the pipe exterior convert thermal energy from hot liquid transport directly into electricity, ensuring that the critical monitoring sensors remain fully powered even during long winter storms without sunlight. Retrofitting thousands of miles of legacy steel pipelines built in the mid-20th century presents a monumental logistical challenge. Engineers do not always need to cut open and replace old steel pipe bodies to upgrade the grid. Strap-on ultrasonic sensors and external smart valve retrofit kits allow technicians to convert older manual valves into semi-autonomous edge nodes, bringing historical energy corridors into the age of real-time digital monitoring without requiring multi-billion-dollar reconstruction projects. Ultimately, the evolution of smart valves represents a broader transformation across modern industrial civilization. As millions of miles of physical pipeline merge with edge-computed silicon logic, the world moved away from reactive manual checks toward an era of predictive, self-healing physical infrastructure. Hidden deep underground, across deserts, and beneath oceans, these intelligent mechanical sentinels continuously listen to the physical pulse of fluid dynamics, safeguarding global energy, drinking water, and ecosystems against sudden catastrophic failure.